Okay, let's look at get combinations. Let's look at get combinations. I like my picture today. It looks much nicer. Looks a lot nicer. Let's look at get combinations. All right. Uh, we already looked at a bit of combinations, but indirectly. All right. Let's just say get combinations. Very few important things that I need to mention here. All right. What I've looked at so far was the let's look examples. We've looked at what? At the NOT gate. We started there. We went on to the AND gate. If I remember correctly, that was the sequence. Yes. Then we went on to the OR gate. Okay. We did later the exclusive OR gate. Alright. Someone could argue that these are the what? The primary gates. If you think of primary colors, I could say this is the equivalent in gate language. Okay, these will be the primary gates. Now, then you spoke of combinations. I remember putting up combination of the what, of the AND and the what, and the NOT, then giving us a NAND gate, for instance. So the first combinations we looked at was what? Combinations of what? Of AND and NOT. And these ones gave us what? Gave us the NAND gate. All right. So this was the basic introduction for what, the indirect introduction to what, to gate combinations. Even though ultimately it was one gate with one symbol like that, this being the AND and the NOT. We ultimately had a gate like this, and it was one gate, not two gates. It was one gate, but what it still meant was that this here is the same as two gates, the AND fitting the NOT, the AND fitting the NOT. So now that is basically what, a combination of gates. That is the first combination of gates. If you look at also there, all right, I looked at the OR plus NOT. This culminated in a what you call the NOR gate. Now again, this was ultimately a single gate, but what we mean here is that this NOR gate can actually be achieved by what? By combining the OR gate, or what am I doing? The OR gate. If you combine the OR gate with the, so this is actually two gates together, this, right? This might be one gate, but you can get it from combining two gates there, all right? Also, despite these two being somewhat different gates, all right, the exclusive OR, the exclusive OR, the exclusive OR and the exclusive NOR might be exclusive gates. They might work in a way that they actually what, they actually look like they what, they actually opposites. But if we did now have an exclusive OR and we added that to a NOT gate, we would have the exclusive NOR. Exclusive NOR. Okay, so what does it tell you? If you put it in symbols, the exclusive OR plus the NOT. Oh, okay, let me just say the exclusive, I want to be consistent with what I've been doing before. The exclusive OR can be seen as a combination of the exclusive OR with the NOT gate, with the inverter. All right, so what are we seeing here? We are seeing that there's something that I also want to point out. Let's suppose we have a one input inverter. All right, I want to say I could combine something else here. I'm going to come to these extra combinations here. So this could be done like that, or let's suppose, let's study something here. Let's take the what, the NAND gate. The NAND gate. If you look at the NAND, the inputs to the NAND if it's a 2 input, it's going to be count 1, 0, 1, 2, and 3. Now let's call that A and B, and let's look at the output. The output for the NAND is, as long as it's not AND, it does not like the AND. As long as it's not AND, it looks out for a 0. Just like the AND gate looks out for a 0, but with the AND gate you get a 0, with an AND gate you actually get a 1. Alright, so now if you look at this, these two inputs, when they are equal, when they are the same, okay, they give you what? And the opposite. If the equal is 0, they give you the opposite, which is 1. If the equal is 1, they give you the opposite, which is what? Which is 0. That actually suggests what? That if we had an AND gate, a NAND gate, and with two inputs, and those two inputs were wired together so that they can just be 1, a 0 here would mean 0, 0 there, and it will give us a 1. And a what? A 1 there. Let me not be lazy and draw it again. A 1 there would what? Would give us what? A 0. Alright, so what does this mean here? It means that I could have said, let me rather move my work. I'm not sure whether I want to move that. No, I don't want to move that. I want to move the rest. Okay, then I say let's move this a little to that side, because I want to show something very important here. What I want to show is this could have been actually what I could have combined here an AND gate instead of the inverter. If I couldn't have an inverter, then I could what? I could actually use a 1 input NAND gate. Okay, a 1 input NAND gate. It will still give me this. Remember, is as good as an inverter. Okay, this is an inverter. A 1 input NAND gate is as good as an inverter. All right, and then also I could also have, let's also prove something else also with the NOR gate. Does the same happen? Let's look at NOR gate A, B, 0, 0, 0, 1, 1, 0, and 1, 1. Now, with the NOR gate, what will happen is we are looking out for 1. O and NOR look out for 1s, and if we have a 1, the output should be 1 for O, is 0 for what? For NOR. There's no 1 here, so for O it would have been what? 0, but for NOR it's a 1. What do you see? Same story. 0, 0 is changed to a 1, 1, 1 is changed to a 0. So if the input, so this could have been that, or it could have been, an AND. Let me rather do this again. Okay, move it on. Or I could say, here's my AND gate, but the other, I could invert that with what? Remember, this is true even for more than one what? More than 2 inputs. Even if it was a 3 input what call this NAND gate, or 3 input NOR gate, it will still give us what? It will still give us inverters. Alright, if they what? If the inputs are wired together. So this here would be, I could invert a NAND as an inverter, or I could invert a what? A NOR, as long as the inputs are all wired together. For right. So now, same story here. This could have been what? An OR gate with an inverter, but in the place of the inverter, if I can't, why do we actually bother with this? It's because sometimes we want to build certain circuits and we don't have the case we want. So we have to be able to what? To find alternative case that will still work. Alright, so this here could have been instead of an inverter, I could have had what? A 1 input, could be 3, could be 4, doesn't matter. As long as the input is a common input for the what? For the NAND, it will work as an inverter. Alright, or an O with so why would I do this again? Because I am trying to find, if I don't find the gate that I want, and I want to know what alternative gates could be used to achieve the same to do the same job. So here we could have had what? We could have had our exclusive OR, the output being inverted with either an AND, which is an inverter, or a what? Our exclusive OR, one input. It's not sufficient to say AND, one input NAND, or one input NO. These work basically as what? As inverters. All right. So this is very critical to know. In the event that I'm looking for an inverter, I can't find an inverter, I could just use what? I could just take any of my NAND or NO, and then I could what? I could actually wire the inputs together and have one input. Then it will work as what? It will still be fit for purpose. Now, if you look at these are combinations. These are the basic combinations. But let's go and say, let me refresh this and say, all right, what about we've already seen how we can combine in making gates that we already knew. Let me do something else here, something that I'll call double negation. Again, as a combination of gates, I'll do double negation. All right, what does double negation do? Let's see. Let's suppose I have a NAND gate and I want an AND gate. I'm looking for AND gates. I can't find them, but I've got an AND gate. What could I do? I could invert that, and this will be equivalent to my what? This will be equivalent to my AND. All right. Same with the what? Same with the O or any other gate, exclusive O or whatever. Let's say I have an O and no, sorry, but I'm looking for an O. I could invert that output. The opposite of the opposite is the what? Is the original, right? The opposite of the opposite is the original. So if my O was inverted for me to get a no, that output could be inverted back to get us a what? To get us back an O. So what does this mean? This will take us back to O. Let's do that also down here with the what? With the exclusive OR. Right, I want to do with all my primary gates. Let's deal with an exclusive OR. Alright, and then let's rather say exclusive NO. If I was looking for an exclusive OR and I couldn't find it, but I could get what? I could get exclusive NOs and inverters. Then I could basically what? I could basically combine them to get, sorry, this is the exclusive OR. I could combine them to get the exclusive OR. Now, what does this mean? This means that if you look at it nicely, if I have, remember, this could have been, in the place of that, it could have been a one input NAND gate instead. Okay. All right. Going forward, I'll just do this through the NAND gate, né? But you know that NAND gate would normally have more than one input, so it means wiring them together. I would basically do this, but it means that if it has three inputs, all you do is wire them all together. All right. So this here is the one input NAND gate, meaning the gates are what are actually wired together. All right. So what it therefore means here is same applies obviously with the other gates. What it therefore means is that since we already saw with the last bit of the work just before this, what we did in the previous page, we said our NAND is actually could be made of a combination of what? Of, maybe I didn't give it enough space. I'm gonna want to write in the middle there. So let me extend it a bit and say I could do this, and this is my NAND, which I started off with, but I am actually going to what, this is the equivalent of my NAND, which is basically that. Now I'm gonna say, if I, no, little more space, I want to write in between. If I invert, what I'm trying to point out here is, if I invert twice, this is double negation now. If I invert twice, I go back to, we say this is, if we invert and NAND, which is the equivalent of this, we go back to AND. So this is going back to AND. All right, this is going back to the AND gate. Now, what do we mean? Let's put it in what, with Boolean algebra. What I'm doing here is I'm saying this is equal to this, A times B is equal to A times B inverted twice. This is what it means. This here is A times B. This is my gate, which is what I end up with. If I invert, I got an end. If I invert again, I go back to the end. So what I'm saying here is double negation is actually what? Redundant. This is what I want to highlight. This. It is also true, obviously, for this. If we take this one here, we would say that is a no. So a no is what? A, let's say, oh, okay. Let me not talk of A's and B's that don't exist here, okay? A, B, in this case here, it's A or B. This says this is my NOR gate, but if I invert twice, it's going to be the same as just the OR gate. All right. Again, I don't know, exclusive OR, that will be A. All right. Now, all right, let's see. A exclusive OR, B. If I invert that, I've got the exclusive NO. If I invert it twice, I've got just the exclusive OR. Okay, this is very, very important to know. All right, this is very important to know. Double negation is very important to know. What does it mean in terms of gates? It means that one gate, this gate here, if I could not get it, and I had what? I had that, I could just invert that. All right, but don't forget that also it teaches us what? That double negation is what is. This is going to be very useful when it comes to what? When it comes to Boolean, solving Boolean, simplifying circuits and solving Boolean equations. All right, it's going to be very, very important. Now, let's go to another page and say, now, if we had gates like, let's take a gate like, let's take a situation like one that I received. Let me check it quickly in my phone. One that I received yesterday. A question that I received yesterday would be something like, let's quickly, just a few minutes, let me see. I'm looking in my phone here. We have something like, okay, not sure why I'm not seeing both, but anyway, we have something like a gate like A, B, C, and we're given an exclusive OR gate. All right, it's an O, and then this, through this we had an inverted A, and we had a B direct, okay, and then we had a NAND gate, and the output from that exclusive OR came there, and then it was NANDed with, nope, it was NANDed with a C, and then the output was in turn fed to an exclusive NOR gate, and exclusive NOR gate, but this side here we had an OR gate which is fed by all three, A, B, and C, okay. A, B, and C went in there, and the output went through. Again, remember this is a NAND gate which will work as an inverter because it's one input. All it means is that the inputs actually wire together. No matter how many they are, they actually wire together, and then the output is fed there. It's a little bit difficult to draw straight lines with the with the pen, and then this here is given as our output. Now, alright, in typical test and exam questions or whatever designs, probably this could have been simplified. Alright, this could have been simplified. Someone could have said, given you the expression and said simplify this, but you could be given a circuit like this and be asked to what? And be asked to work out the what call this? The expression, the Boolean equation for it. I'd like to call it an equation because this Z is equal to, okay. So the starting point here, what's the point of not starting right there? Because this is the top gate. All right, if we look there, our input there is not A, meaning that there's an inverter for A. All right, now the other one is B. The other input is B, but they go through an exclusive O. So this is A exclusive O B. All right, that's the output from that gate, which is fed there. So therefore, I might as well go on with it and say that, but it's now an input, so I will bracket it together. It's going to be NANDed. It's a NAND, so it's going to be a NAND with C. This would have been an AND with C. It's a NAND with C. All right, we come here A, B, C. This is simple enough. This is A or B or C. Okay, this is an inverter. All that will happen is the input is going to be inverted. What's the input? A or B or C, and we know a one input one is going to be what? It's going to be a mere inverter. All right, so it's going to be a line on top. So the output here is basically that went in. We will take it as it is. It's not A or B. It's dangerous to not have the bracket because this is not, remember, this is not equal A, not A, not A or B in brackets with C. Just like in mathematics, if we were multiplying, you cannot just drop the bracket and say this cannot be equal to not A. Some people tend to drop that bracket and then they've got something like this. You know, mathematical, that is dangerous. You cannot have something like that. So you cannot have 7 plus 2, all of it times 3 is equal to 7 plus 6. It doesn't make sense. So you literally cannot drop the bracket. All right, you cannot drop that bracket. Now that, going back there, so that was our input there with the NOT. This is our input, but input into what gate? That gate. So I'll come back to that gate. This is what? This is an exclusive O. I'll put O for now, and then the other one is that other is the what? Is A or B or C NOT. Now these together, this is not an exclusive O, it's rather a NO. So there is our exclusive NO. All right, the two inputs being that and that. So coming up with the what? With the expression should be fairly easy. All right, when a person understands the gates, coming up with the expression is actually fairly easy. You could, however, be asked to be given this and be asked to what? To try to what call this, to work out the what? To work out the circuit, okay, the circuit diagram. Now what you then do is you have to start in there and go backwards. All right, You could also be asked to what? You could also be asked to simplify this. Probably you may find that some of these cases are not even necessary here to actually you find that these are not even necessary. But before I do that, there's something else that could be what. Let's see if you can copy. Let's start there. Let's say we want to copy them. How would you copy? We'll say okay, we have three inputs: A, B, and C. What do I see? I have node A, so I could have what? This is actually what that means. It means an inverter. So I could have a node A there. I could take my node A and say I also have node A after inverting. All right. I could say, but this is what this is, and I can't start outside. I have to start with inside here. There is a bracket there. We can't separate that. So for that bracket there, what do we have? Not A or B. So it means we have an OR gate. It means we have an OR gate. And the input there is not A or B. Okay? That there, this here could have just been a little zero in front of thing, which is the same obviously as what? As that there. Alright, what am I doing? The gate that I'm doing here is the OR gate. Alright, so I'm actually, I think I may have gone the wrong route here. I may have gone, no, I've done something wrong here. This was, no, we got lost here. We lost our little round here. We lost that this is an actually exclusive OR. It affects a lot of our thing there. So that there is actually exclusive OR. Okay. No. So this here is actually wrong. What am I doing? This is exclusive OR, and this here cannot therefore be that gate. No. Okay. This was us sleeping. We forgot that it was exclusive OR. We just made it OR here, which was wrong. The input was that. We shouldn't change that input. So this here is actually exclusive OR. Okay. So what I'm saying is we could have had a little zero there. Alright, we could have had a little zero there. That was very careless. Now we come and say, okay, what is this here? It is node A is an exclusive OR with B. And yes, it's right. We had forgotten that part. That was wrong. Okay. Now, that output there is fed through a NAND gate. So this is fed through a NAND gate. Oh, I hope people were watching and screaming there. Shows the people must have been awake. It's a NAND gate with a C. So the C. So I want to repeat that this could have been, the not A could have been a simple zero. There's nothing wrong if we put a little zero there. There's nothing wrong with doing it like this. There's nothing, it actually means that, and there's nothing wrong with putting a little zero in front instead of drawing the inverter. It means the same thing. All right. Then we proceed and say, what do we have now? We have whatever came in, which was not A, exclusive OR B. Okay. These together is going through a NAND. We'll start with AND, and it's a C. An AND is actually what? An AND is actually an AND with a line on top. So that is what we have there. This part there is done. Right. On the other side, it's gonna go through an exclusive OR gate. Exclusive NOR gate. So we can see it's going to go through an exclusive NOR gate. This is the final gate there. But what's going in, the other input is what? Is A, B, or C. No. So this is what? A, B, or C. And it's an O. No. Remember that there's nothing wrong again if someone had done what? Had done that. Okay. We had done the O, then the not. There's still nothing wrong there. It actually means the same thing. All right. So yes, if you couldn't find the NOR gate, you wanted to build the second and you couldn't find the NOR gate, you could replace that. There's nothing wrong again if you had made a what? A one input NOR or NAND in the space of what? Of the inverter. Alright. Anything that is correct will be acceptable. So yes, we could have done that, but we have no way of knowing it was 2 gates by merely looking at it. We have no way of knowing it was 2 gates. The way it is here, it doesn't tell you it was actually made out of 2 gates, right? It doesn't even tell us that there was a what? There was a NAND instead of what? Of a NOT. It doesn't even tell us that there was a what? There was a NAND or NOT instead of a what? Of a NOR, for instance, okay? Of a one input NOR. So that's why I'm saying it could have been what? It could have been the OR with a NOT, the OR with a NAND as it is there, and the OR with a what? With a NOR as with one input, and all of them would actually be what? Be acceptable, because it's what? It's actually true. All right. Unless there was a provision that, in the place of what? Of inverters, please use what? Please use no one input NORs or NORs. Just say no, because it's actually a part of helping with the answer if you're going to be told it's one input. So it's just say no. Then we don't see inverters in the place of inverters use no. If there was a provision like that, or use not on NAND, then you obviously would have then to what? If they said NAND, you'd have to do this. Said no, there'll be a no in this space. If they didn't say whatever, what works will be fine. So then we take this through to what? This will go through. If you look this gate here, after this NOR gate, we go straight to the what? To the exclusive NOR, and there is our Z. It might look a little bit different, because when you have a statement like this, it is not very clear what actually was the original situation. As long as it will be something that works, and then it will be fine. There's nothing wrong. So yes, we can be given a statement and be asked to produce a circuit. We can be given a circuit and be asked to produce the statement. All right. The last part that I would like to do with this very same example is actually what? Is actually the what? How to draft a truth table with this. All right. The truth table, you would remember that number of combinations for a truth table, number of combinations is actually given by what? Is actually given by 2 to the power of n, where n is the what? Where n is the number of input, where n equals to number of inputs. Alright, so we have 3 inputs here, A, B, and C. So we have what? We have got the count 0 up to 7, which is what? Which is 8 combinations. Which is our 8 combinations. 0, 1, 2, 3, 4, 5, 6, and 7. And this is our A, our B, and our C. So there would be our output. Now then, we'll have to say to ourselves, all right, do we really put the output there? Would it be easy to work out the output? Yes, you could, but it's not going to be easy that way. All right. So it's best to actually what? Put the stages there first. So our first stage will be A or B. If they say do that, you say, okay, we've got, obviously, I've got a NOT A. I can see I've got a NOT A. That part is easy. Why? Everything that is A is inverted. So that will be 1, 1, 1 for the 4 zeros, and that will be 0, 0, 0, 0 for the subsequent 4 ones. Then we'd have to look and say the next one is what? Not A, exclusive or B. Now you come and say, I know not A is this, it's exclusive or to B, so I'm looking at these 2 columns here. We know that the exclusive or must have 1, 1 is equal to 1. The symbol says equal to 1. So it must have 1, 1, not 2 ones. It must have a 1 and there must be 1. So let's look there. There is 1, 1, 1. There is 0, 1, 1, 1, 1. There is 2 ones. B is 1, not A is 1. Nope. There is 2 ones again. B is 1, not A is 1. Nope. Then there is 2 zeros for B and not A. 2 zeros again, B and not A. So both of them, nope. Nope. There is 1, 1, not, B is 1. Yes. 1, 1, B is 1 again, not A is 0. Yes. So these are what you could have looked at that. You could have looked at it like that. But a much easier way for me would have been to say this is an equality comparator. This is a what? Over what are we doing? It's a inequality comparator. It's actually the exclusive or. So it's the inequality comparator. If you look at not A and B, not A and B, are they equal? No. Is inequality? So yes. Again, are they not equal? So it's inequality? Yes. Here they are equal, so it's equality, so it's no. They are equal again, 1, 1, 0, 0, 1, 0, 0 again. So that's all no. They're not what? They don't obey the inequality. They are all equal. And then there, it's 1 and 0, they are what? They are in unequal? Yes. 1, yes. As long as they're not equal, as long as B and not A are not equal, you have an output. So that's an easier way for me to actually run through it, right? Then if you look at the next stage there, the next stage is actually we have a get like that to be A or B or C not. Okay, now if you have a get like that, what do you then see? You then see that you need to look at, if you are looking at an OR or a NOR gate, you are looking out for ones. We've been saying this forever. So if there is a 1, the OR would have been a 1, the NOR would be a 0. So we come and look at A, B, or C, no 1. So the OR would have been a what? Without a 1, the OR would have been a 0, but it's a no, so that's a 1. All right. Then if you come and look at this one here, there is 1, 1, 1, 1, 1, 1. The rest of it is ones. If it was all going to be ones, but it's no, so it's all going to be zeros. Remember the and then they look out for zeros there, or looks out for one. So because there's ones, it's all going to be zeros. Now, if you come and look at the other gate, this one, if you go back to this one here, is the not A exclusive OR B together NAND C. What do? I look at this and see this is that and C. So I look at that column and that column there. All right. If I look at those two columns, all I look at is this is what? This is a NAND gate. NAND gate looks for what? NAND gate looks for zeros, and then they look out for zeros. Then AND would give you 0. Anything times 0 is 0, but NAND will give you 1. So if I see on C, if I see a 0, I know I'm going to have a 1. Again, a 1. The C is skip 1. 1, skip 1, 1, skip 1. So all that is going to be 1 because there's zeros there. As long as you see a 0, AND would have been 0, but NAND will be a 1. I come to this one here, that one there, and if I see zeros, there is a 0, it's already got a 1 from the C. That doesn't have a 1, we give it a 1. That already has a 1 from the C. That doesn't have, we give it a 1. And then everything else is therefore zeros. Okay, so then what do we have? Ultimately, we have the whole gate, because we've done everything here. We've done that part. So we've got these two parts now. They are done. Now they go through the final gate. But fortunate for us, they give us their output. Now, therefore, all I do is look at these two gates. Is the exclusive what? No. Therefore, it's an equality comparator this time. If this and that, if this part and that part, this part and that part are equal, it's an equality comparator. We are going to be happy. So we are happy they are equal. We are happy they are equal. They are not equal. They are not equal. Not equal. Not equal. Not equal. They are equal. So what has happened here is that these three are the only position that give us what? That give us outputs. The rest are what? Yes, I could have looked at what? I could have looked at the exclusive OR. I could have looked at them being equal. I could have said, okay, remember, if it's OR, if it's exclusively OR, the OR would have given us, the exclusive OR would have given us what? Would have given us a 1. The exclusive NOR would have given us what? A 0. Still, you'd have arrived at the same conclusion. All right. So, we've seen how we can have a circuit and derive an expression. We've seen how we can have a what? An expression and derive a circuit. Okay, and the two circles must be the same. Obviously, I did that on purpose so that we can actually correct ourselves. All right, but then also we are seeing that we can actually use the expression or the circuit to actually get us what? To actually get us a truth table. Now the question that remains is, well, it's good practice. It's just that it's difficult here to what? To actually draw lines here. It's good practice to have lines between the what? Between each these are columns, so it's a table. So it's good practice to have lines running across and lines going down. But then hey, it's tough to do that with the what? With a pad. So I'm not leaving it because it's the best thing to do. I'm leaving it because it's difficult to do in under the circumstances, but you must do it. Right. Then if you look at now we've got a truth table. Can we, if we could derive a truth table from either one of these, can we then make a what? Have used the truth table to actually design the circuit? And the answer is yes. We'll look at that later when we're looking at what? When we're looking at circuit design, where we'll be looking at what? A SOP, sum of products, versus product of sums. All right. We can use these two. We can look at that and actually what? And actually derive come out with our circuits or our expressions. Yes, but then what is worth noting here is that the SOP and POS, when you're using the truth table, you will not get to all this jargon here. We didn't try to clean out. We didn't try to simplify and get the simplest gate combinations that would give us the same output. So what happens is that the truth table, actually when you use the truth table, you're actually going to get the simplified version of that gate. You won't get this gate. It's very rare that you'd find the gate as it is. Usually you would find a simplified version of the what call this, of the gate, okay, of the get sequence. All right, or the expression. You may find a simplified expression. When you work out the expression, you will find a simplified expression. All right, so SOP and POS, yes, will give us the equivalent of these two. They will not give us the what. This is seldom that it would. It could, but it's very, very seldom. All right, that being said, I hope I'm appreciative of the attention. I hope it wasn't too long, and I hope people enjoyed this as much as I'm trying to. All right then, ciao.